Today we're going to do a review of logarithms, something you've definitely learned before, pre-calculus 12, but we need to review it before we go any further in calculus. So, should all be review for you. We can go through this fairly quickly. Big question here, what's the inverse of an exponential function? Well, let's start by actually graphing this exponential function, and by now we've done that a few times. You should remember more or less what it looks like, but if you don't, we'll just plug some values into the x, like 0, 2 to the 0 is 1. So 0, 1's a point. Put 1 in there, you get 2 to the 1 is 2, so 1, 2 is a point. Put 2 in there, 2 squared is 4, so 2, 4 is a point. Put 3 in there, 2 cubed is 8, so 3, 8, and that's as high as you can get. If we go down this way, negative 1's a flipping negative, so it becomes 1/2. If you put negative 2 in there, you flip and square, you get 1/4, 1/8, 1/16, and as you know, this is going to get closer and closer to the asymptote, which is the x-axis, as we go down towards negative infinity. So very hard for me to draw, but basically it looks something like this, and then it goes up very quickly because it's exponential. Okay, that is y equals 2 to the x. So now the question, what's the inverse of an exponential function? So let's find the inverse of this exponential function right there. How do we do that? Well, when we find the inverse, the first thing we do is wherever we see y, we put x, and wherever we see x, we put y. So you get x equals 2 to the y. Then the next thing you do is you isolate the y. Well, before you learned about logarithms, that's just not possible. So I'm actually going to put right here, can't isolate y. Alright, well, we want to graph it, so why don't we do this? We'll make a table of values, we'll put our x and y, but do you see it would actually be easier to pick some values for y? If you put x values in here, like say an x value 3 for example, 3 is small, easy number, right? No way, 2 to the what equals 3? That's really, really difficult. So what you want to do instead is pick some numbers for the y. Let's go from like -3 up to 3. So there we go. And if we do that, and remember we're putting into this y here, we have 2 to the -3. Well, 2 to the -3, that's a flipping negative, so you get 1/2 cubed, and that is an 1/8. And if you do -2, it's a flipping negative, and then squared, you get a 1/4, then you get a 1/2, then you put 0 there, you get 2 to the 0, which is 1, 2 to the 1 is 2, it seems somewhat familiar, doesn't it? 2 squared is 4, and 2 cubed is 8. I'm sorry, some of my numbers are hard to read. So if we graph that, 1/8, well, that's barely anything, and -3. And then a 1/4 and -2. And a 1/2 and -1. And 1, 0. And 2, 1. And 4, 2. And 8, 3. And here we go. This is coming up like this. And this is getting closer and closer and closer to the asymptote, but never getting there. What's the asymptote this time? It is the y-axis. Was the x-axis before, and now it's the y-axis. Now, how come you can be confident that this is the inverse to y equals 2 to the x? This is y equals 2 to the x. How come you can be very confident this is the inverse? Because if I draw this line from corner to corner, what do we call that line first of all? What's the equation of that line? Equation of that line is y equals x, and what you've learned before is when you draw, if you reflect, a function over that line, the y equals x line, you get the inverse function. And you see that these two curves we've drawn here are totally mirror images of each other. So the blue one is definitely the mirror image or the inverse of the purple line. Now, what was this one? This one was x equals 2 to the y. But we want another way of saying that. So this is where the idea of logarithms come in. Basically, a logarithmic function is simply the inverse of an exponential function. In general, we write y equals the base b logarithm of x rather than x equals b to the y to express the inverse of y equals b to the x. So this is the key right here. This is what we like to write. Instead of writing it in this form that I did here, this x equals 2 to the y, how I'd write that instead, which is more easy to work with, it's more accepted, it's more usual, is I would write y equals the base 2 logarithm of x. This is the same thing as what I've written here previously. They're exactly equal to each other. So as I've already said, the way you say this is the base b logarithm of x, or if you want, the other way you could say it is the logarithm to the base b of x, whichever way you want. That's how you say this highlighted bit here. And a little bit more for you here. I've just written the same thing. Y equals the base b logarithm of x. We have some restrictions. X has to be greater than 0, b has to be greater than 0, and b also cannot equal 1. Okay, let's name these things for you. This y value, whatever value you have there, this is called the value, but the best way to probably think of it is this is the exponent. Okay, when you're talking about logarithms, what you're talking about is like an unknown exponent that you're trying to figure out. So we'll talk about that in a second. The b here is, just like the letter would indicate, the base, and the x is called the argument. So as I said here with the value, also think of it as the exponent. Think of the logarithm as the exponent to which the base b must be raised to give x. So for example, I'll just write a quick example here. If I had the base 3 logarithm of 27, what I'm asking myself is, what exponent do I have to raise 3 to get 27? Does 3 to the first power equal 27? No, that equals 3. 3 to the second power? That equals 9. 3 to the third power? That equals 27. So it's equal to 3. One more example of that. How about the base 5 logarithm of 25? Well, what do you have to raise 5 to get 25? You have to raise it to the second power. So the answer is 2. Okay, let's go ahead and write some of these in logarithmic form. So what you would have is, remember, the value here, I think of as the exponent. So the exponent is 4. 4 is equal to logarithm. Now, the b is the base. Well, in this, what's the base? The base is 5. It's also the base here, 5. So that's nice. And then the number left over, this is the 625. That's the argument. So we have 5 to the fourth power equals 625. 5 to what power equals 625? Oh, to the fourth power. This is your exponent. Okay? Again, exponent goes first if you want. So 1/2 equals, then we have logarithm with a base of, well, the base here was 81, so it's still 81, and then our argument is 9. This is saying that 81 to the what power equals 9? Well, you have to take the square root of 81 to get 9, and square root is the 1/2 power, so that makes sense. Perfect. Let's go the other way this time. So we've got our logarithmic form. Let's put it in exponential form. Well, we'll start with the base. Remember, the base is the little one right here. So 3 to the exponent, exponent's the one by itself, so 3 to the fifth equals 243. Is that true? Absolutely. 3 to the fifth power does equal 243. Same here. Start with the base, which is 2. Then you put the exponent, which is -3, and that equals the argument, which is 1/8. Is this a true statement? Yep. This is a negative exponent. Flip it over, cube it, you're going to get 1/8. Okay, let's solve some logarithmic equations here. So a good thing to do here is to put it into exponential form. So in exponential form, this would be the base 4 to the exponent 3 equals x. Well, if x is equal to 4 cubed, x is equal to 64. That's how much 4 cubed is. Similarly here, we would have the base 64 to the exponent 1/6 equals the argument x. So x equals 64 to the 1/6. Well, that's the same as the 6 root of 64. You know what that equals? 2. Similarly here, exponential form, the base is b, raise it to the exponent 3, and we get 27. Now, there's a couple ways you could take it from here. One way is that you could turn this 27 into a power. What's 27 as a power? It's 3 cubed. Well, if b cubed equals 3 cubed, then they have the same exponents, then the bases must also be the same. So b has to equal 3. The other way you could have answered this, or if you could have solved this, what could I raise this to in order to be left with just b here? I could raise it to the 1/3, because 3 times 1/3 is just 1. What I do to one side, I have to do the other. So I raise 27 to the 1/3. Well, that's the same as the cube root of 27, which is equal to 3. So whichever way you like. There's probably other ways you could do it. Just do it in your head as well. Probably some of you don't even need to do this at all. Okay, same here. Exponential form would be b to the 1/3 equals 5. Okay, here's one where you definitely will probably want to do the second method I used here. What would I have to do to make this just b on this side and not b to the 1/3? I'd have to multiply it by 3, because 1/3 times 3 is just 1, and that's what I want. What I do to one side, I have to do the other. So I end up with b equals 5 cubed, and 5 cubed is equal to 125. Okay, 2 to the y equals 1/4. The way I like to do these ones is to write the argument here as a power with a base of 2. Is that possible? Yep. 2 to the negative 2. So we have 2 to the y is equal to 2 to the negative 2. Well, they have the same base, which means the exponents have to be equal to each other. Y is equal to negative 2. 8 to the y equals 2. Again, let's try to get the same bases here. So we could write this one as 2 cubed to the y equals 2. Well, the rule is with power of a power, you just multiply. So you get 2 to the 3y equals 2. Might as well put a power here. This is 2 to the y, sorry, an exponent here, 2 to the 1. Well, they have the same base of 2, so the exponents have to be equal. 3 to the y, 3y, sorry, 3 times y has to equal 1, which means 1 equals 1/3. Okay, here's some laws of logarithms that you learned before. The base b logarithm of x times y. What's that equal? It equals the base b logarithm of x plus the base b logarithm of y. This is one of the most useful things about logarithms, if you don't have a calculator, is that you can turn multiplication questions into addition questions. Okay, very similar to that. The base b logarithm of x divided by y is equal to the base b logarithm of x minus the base b logarithm of y. And finally, the base b logarithm of x to the r power is equal to r times the base b logarithm of x. So those are 3 rules you've seen before, and you definitely need to know them in this chapter. So we're going to use those laws just to rewrite these. I'm going to expand this one out. So you can see we have 2 things multiplied together here, the x cubed and the y6. So we're going to use the first rule to expand it first of all. You can see we can turn it into addition statement. So we would have the base 5 logarithm of x cubed plus, rather than multiplying here, we can plus with separate logarithms, the base 5 logarithm of y to the 6. And now we can use this last rule here where we see we can take the exponent, and I don't know how I came up with this years ago, but I scuttle it out to the front. Scuttle's like, you know how a crab moves, it kind of scuttles along. Well, it scuttles out to the front here. I know it's ridiculous, it's not funny, but I've just always said it. So the 3 comes out to the front. You get 3 times the base 5 logarithm of x plus the 6 comes out to the front, scuttles out to the front, 6 times the base 5 logarithm of y, and there's your answer. Okay, let's do similar here. We actually have 3 pieces here. We have the a, the b, and the c on the bottom. So they're all going to be just logarithm. What base does that mean? It's base 10 if it doesn't say. That's called the common logarithm. If it's base 10, you just don't need to put the little 10 right here. You can put a 10 there if you want, but it's actually not necessary. So we have the base 10 logarithm of a. Now this is multiplying, so it's going to be plus the base 10 logarithm of b, and then we're going to minus, because this is division, the base 10 logarithm of c, and since it's actually cube root, we're going to put that to the 1/3. Is there anything else you can do? Yes, there is. That 1/3 can scuttle out to the front. So we have the base 10, or common logarithm of a, plus the common logarithm of b, minus 1/3 comes to the front, 1/3 times the common logarithm of c. And finally, we're going to do the opposite. We have one that's all expanded out here, and we're going to put it into a single logarithm. So you can see we have 1 piece, 2 piece, 3 piece here. So I think the first thing we should do is just backwards of what we did here. Remember the last thing we did here was deal with these exponents. Now we should deal with these exponents first, the 3, the 1/2, and the 4. So we'll have the base 2 logarithm of s, and the 3 scuttles back here, and you get a 3 there, plus the base 2 logarithm of t, but the 1/2 scuttles up, minus the base 2 logarithm of t squared plus 1, and the 4 scuttles up to the top there. Now we're going to put it all into one logarithm. So we have the base 2 logarithm of s cubed times t to the 1/2, but why don't we write that as square root of t, because that's what the t to the 1/2 means, all over, all divided by, because this is minus, so it's going to be division in the single logarithm here, t squared plus 1 to the 4th power. And I don't know if it helps you understand this, but this is all base 2 logarithm of all of that, right? And there you go. There's your little short reminder of logarithms. Hopefully you remember a lot of it.